post this tonight later. Okay, got it. Perfect. All right, there we go. There we go. So let's take a second to look at the supplemental information that you will get at the exam. Okay, so let's look at it. Okay, supplemental information packet. So here we go. So as always, the periodic table. I always get a kick. Sometimes I read how you guys write my name, an instructor name. I just like to see, no one really looks at these scratch papers ever, but I think it's just funny to see how people spell my name, or if you just put DrN, that's the smart thing to do. So here are the conversions. So same exact conversions from midterm 1. I'm just continually adding to this. And so you see all of the pressure conversions are given: 1 atmosphere, millimeters of mercury, torr, Pascal, and PSI. All right, so all of those equivalencies are there. For the most part, if you're using PivNert, you want to be working in atmospheres. But if you're just using the combined gas law or something, it's fine to stay in whatever unit's given, but then convert to the appropriate one depending on what the question asks. I give you 2 different versions of R, the energy version and then the gas law version that you see there. Speed of light, Planck's constant is there. Here we see the conversion between Kelvin and degrees Celsius. Celsius to Fahrenheit in case you need it. There's density, molarities, percent yield, and then our gas law constants, some ideas about the partial pressures and mole fraction if you have a gas mixture. We have the most probable speed equation, which really just tells you trends. We see that most probable speed increases when temperature increases or when the molar mass of your gas sample is lower. Speed of light calculations, energy of the photon, what's that one? The de Broglie wavelength, uncertainty principle, and then finally Z effective. So I give you basically every equation. What you probably should memorize are all of those shapes. But to me, I don't find that to be memorization because the shape looks like what it is. If it's square planar, it's a square and it's flat. Trigonal planar, it's a triangle and it's flat. I mean, tetrahedral, octahedral, some of those names, are specific, but definitely know those. I would memorize Avogadro's number. That was from midterm 1, but that's still an important concept in chapter 5. Do you remember Avogadro's number? Yep, 6.022 times 10 to the 23. October 23rd is mole day. They call that day mole day because 10 to the 23, just so you know. So if you want a reason to celebrate Halloween early, that'd be cool. All right, so let's get started. What chapter do you want to start on? Or you just want me to go in, or yeah, what? 5, okay, so you just want me to go in order? Okay, all right. But here's the thing, 5 is all the math. Y'all do good on math. All right, you have comfort in math. It's the concepts that can get you. So let's make sure we spend some time on concepts. Okay, the first one, we have a high altitude balloon. Here's the volume at that temperature, at this pressure. What is the volume at 20 kilometers in the air that has a new temperature of -48 and this pressure? What equation should we use? PV. Should we use PV equals nRT here? No, which one should we use? The other one, the combined gas law. But here's the thing, the combined gas law actually is the ideal gas law just set to an equivalency because the sample of gas is not changing, NR is staying constant. So we're just saying, okay, the pressure, volume, and temperature at one condition is equal to the pressure, volume at the second condition. That's all we're saying. So in this case, what are we solving for? V2, that is what we're solving for. What is the new volume? We just got to be careful and make sure that our units work out. So volumes, let's just keep those in liters. Temperature, can we keep those in Celsius? Nope, they have to go into Kelvin. So 21 Celsius, so 273 plus 21. You can put more sig figs there, but 3 sig figs is enough since all the other numbers have 3 sig figs. What I'm saying is what is this number? Plus 21. Whether you put 294 Kelvin in your calculation or 294.15 Kelvin in your calculation, you're going to get the same answer because one has 3 sig figs and that's enough. The other one has 5. You'll be a little bit more accurate with the 0.15, but not enough to make a difference. So that's the number for V1. All right, and then T1, or no, that's not V1, T1, sorry. And then T2 is 48. I have the key right here. Why am I doing it? T2 is 225 Kelvin. Again, the 0.15 is not going to make a big difference. I have to convert pressure so they match. I'm just going to convert both of them to atmospheres, or you can convert both of them to torr. It doesn't matter. You'll get the same answer. And so this pressure, so 63.1 torr over 760 is 0.0830 ATM. So high up in the stratosphere, cold and less pressure. And so we just solve for V2. So setting this up, 1.01 ATM. Initial volume, 1.41 times 10 to the 4 liters over T1. So again, this is in Kelvin, 294 Kelvin equals that new lower pressure in the stratosphere. V2 is what we're solving for, and then T2 is 225 Kelvin. And then solve for V2, right? So temperature is going down, but pressure is also going down. So we can't really use the, Boyle's law or Charles' law here. But we can account for both of them at the same time in Charles' law, because we actually see that they do opposite effects. But it looks like here that the pressure is the more dominating effect because our balloon increases its volume to 1.31 times 10 to the 5 liters. So it increases an order of magnitude. So that's kind of neat when they fill up a weather balloon on the ground with like normal atmosphere. Once it goes up into its place high up in the stratosphere, that weather balloon, it real big because of that reduced pressure. Isn't that kind of cool? Yeah, all right. Or like a blimp or something. Fill up a blimp on Earth. If it goes up into the stratosphere, it'll get real big because of that reduced pressure. Okay, are there multiple versions of what? Of this packet? Of the exam? Of this packet? No, this packet is, there's just one version. Are you looking at the lab review? If you're looking at the lab review, that's the wrong packet. This is the midterm 2 review, so I'll just show where I got this. It's in exam resources, and so for my midterm 2 review session, so again, remember there are 4 practice exams for you to choose from, and then this is the review session. Oops, I forgot to fill in that link. That's my bad, but there's the link right there. Also, and so this is the packet. Again, this is not for lab credit. This is completely optional. This is just for your own benefit. But here's the thing, who writes the exam? I do. So yeah, it's in your best interest to hear what I have to say and what I think is important. Okay, let's keep going. All right, so that was the combined gas law. And so yeah, this is the midterm 2 review with DrN. That packet. Okay, so gases are sold in large cylinders. What pressure in atmospheres is exerted by 2.5 kilograms of oxygen gas when stored at this temperature and this volume? Okay, what equation should we use? Should we use the combined gas law again? Nope, because the sample is not changing. I want to describe one sample at one condition, so I actually want to use Pivnert here. I want the pressure. I was given the volume. R is a constant. I'm given the temperature. So I need to get N. How many moles of gas am I shoving into this container? And so I'm going to use that volume, or sorry, that mass that's given here, 2.5 kilograms. So 2.5 kilograms of oxygen, but we got to be careful. This is kind of like midterm 1 review stuff. If I say oxygen gas, what am I talking about? O2. Yes, I'm talking about O2. And so to convert kilograms or a mass into moles, what property are we going to use? Molar mass. And so the molar mass of oxygen is, I didn't give it to you, but you can look it up with information at your fingertips, the periodic table. So what is the molar mass of O2? It's not 16. 32, it's 16 times 2 because there's 2 oxygen atoms, so it's 32 grams per mole. So I'm going to go ahead and convert that into grams. And this is common. I mean, when we weigh things, usually we want to use like reasonable units, a kilogram amount, a pound amount. Those are like typical units. When you go and fill propane cylinders, they do it by the pound, and that's more reasonable. But we can convert that pound amount into a volume amount. So whenever I always go to the Goodwill to fill up my propane tanks, and they have a conversion chart right on the thing. I like to watch them behind the blast shield. I like to watch them, and they have a conversion between pound amount, because that's what they weigh when they fill the gas tank, to what volume they actually charge me for. So small thing there. So there's our gram amount. Let's convert that to a mole amount. 32 on the bottom, 1 mole up top. This sample actually contains 78.12 moles of O2. So this is N in PivNert. And so we just go ahead and plug and chug. We're solving for pressure equals 78 moles times R. Which R am I going to use? The 8.1 or the 0? Yeah, the other one, the small r, 0.08206 liter ATM mole Kelvin. The unit of R tells you what units everything else needs to be in. So we got moles, Kelvin temperature, what's 22 plus that? 295 Kelvin, I think. I don't know, I didn't write it in there. I think it's 295 Kelvin over the volume of our cylinder, so 40 liters. And then that is our pressure. Our pressure is something like 47 atmospheres. High pressure in our tank. All right, okay, so there's that one. Let's do another one. Okay, mole fraction, where we have a mixture of gases. So the idea is, okay, at STP, 1 mole of gas, at STP, if you put 1 atmosphere, 0 degrees Kelvin, or 0 degrees Celsius, and 1 mole into PivNert, you see that 1 mole of gas equals 22.4 liters of volume. It does not matter what the identity of that gas is. It could be neon gas, argon gas, whatever. And so what we see here is, if you have a mixture of gases, the mole amounts of each gas contributes a partial pressure into the container, but then those partial pressures add up to the total pressure of the system. Because we can think of, all right, we have a mole amount of nitrogen in this sample, we have a mole amount of neon in the sample, and then we have a mole amount of argon in the sample. Each of those have a partial pressure, but if we combine all of them, we get the total pressure that relates to, or sorry, a total mole amount that relates to the total pressure. So we can think about the mole amounts individually for partial pressures, or the total mole amount to get the total pressure. So we just need to kind of consider all of these gases separately. So if I have 2.8 grams of nitrogen, a nitrogen atom is, I think 28 grams is 1 mole of nitrogen. I think I try to make these numbers easy. So there is 0.10 moles of nitrogen gas in this sample. Then let's look at the helium sample, so 0.403 grams of hydrogen. The molar mass of hydrogen is something. What is it? It's like 2 something. It's about 2 grams. Okay, what is it? 2.016 grams is 1 mole of hydrogen. So these are all things from midterm 1, so like mole conversion, so still very important now. So there's about 0.2 moles of hydrogen gas in this sample. So we see that hydrogen is going to contribute twice as much partial pressure than the nitrogen sample, if we wanted to convert those into partial pressures, because there's twice as many hydrogen atoms or hydrogen particles present in this sample. And then finally, argon, which is about 80 grams, is something like, what's argon? Argon, it's like 40. It's about 40, so what is it? 39.95 grams is 1 mole of argon. So it looks like there is 2 moles of argon present. So without doing any calculations, which gas has the highest partial pressure? Argon, yeah, because it has the most moles of gas. So which gas sample also has the largest mole fraction? Also argon, because the mole fraction of argon is going to be 2 over, what, 2.3 moles? And that's like 80-something%. All right, 80% of our sample is argon. So that means 80% of the pressure of this vessel is going to be argon. So if we want the total pressure inside the vessel, we could calculate the partial pressures of all of them individually, add them up, but I don't want to do that. That's a lot of work. So I'm going to do the lazy way and just add up all of these mole amounts, because PivNert don't care what gas it is. It just wants the total number of gas particles. So the total mole amount of junk we have here is, I guess, 2.3 moles of stuff. And then we can just PivNert that, and that will give us the total pressure. So total pressure here is going to be equal to the 2.3 that we just got times R times the temperature given, what is that, 298 Kelvin, over the volume, so 10 liters. And so we get that this sample is about 5.62 atmospheres. All right, so basically just collectively add up all of those mole amounts. All right. I know you all are good at math, but then the concept part, let me show you a concept. I did this in office hours, but I like this example. Okay, what if I had this gas? 1, 2, 3. All right. Here's my gas sample. I have black balls and pink balls. What if I told you that the partial pressure of the pink balls is 1 atmosphere? Tell me, what is the total pressure of this container? I don't need to tell you a temperature. I don't need to tell you a volume. What is the total pressure of this container? So if the pink balls are 1 atm and there are 2 pink balls, how many total balls are in the container? 1, 2, 3, 4, 5, 6, 7, 8. So the total pressure is going to be 4 atmospheres. And for completeness, let's just get, what is the partial pressure of the black balls? 3 atmospheres. All right, and so this kind of highlights the idea of mole fraction. What is the mole fraction of the pink balls? 25%, or 0.25, yeah, 25%. And then the black balls are the remaining 75%. So what you see is that the pink partial pressure is 25% of the total, and the partial pressure of the black balls is 75%. And so that is related to the ratio of the particles actually present in this gas sample. And so that highlights conceptually what, how partial pressures of mixtures work here. All right, okay, perfect. Okay, keep going in order. Yeah, all right. How many pages? 13 pages, ugh, all right. Okay, which of the gases have this density at these conditions? Okay, so what's probably the easiest? How would someone say how they would approach this question? Density of these gases. Anyone have an idea? No, you just want me to tell you? How would you do it? Take 1 liter of the sample. So then how would 1 liter of the sample help us here? Grams. Okay, so if you have 2.104 grams, how would that help us figure out which one of these it is? Yep, you can solve for the mole amount and then calculate the molar mass. Yeah, we could do it that way. Yeah. I don't want to do it that way though. Is that okay? I'm going to just calculate the density of all of them. It's not that bad, I promise. So this is my strategy. Instead of assuming I have 1 liter of gas, I'm going to pretend I have 1 mole of gas. All right, not that different. We're just making a different assumption. You assume, let's start with 1 liter of gas. I'm going to assume, let's start with 1 mole of gas, because that number is very easy inside PivNerd, right? 1, N is 1, that's easy. With that information, I can calculate 1 mole of gas occupies a certain amount. So what's my temperature? 303. And then our pressure is 1.31 atmospheres. So the volume of this gas sample that contains 1 mole is something like 18.9 liters, right? So this number, so this is 1 mole of gas, okay? Any gas sample, as long as you have 1 mole, will occupy 19 liters. So all of these gas samples can occupy 19 liters. So let's calculate what is the density of helium. If we start with 1 mole of gas sample, density is mass over volume. I know the volume of 1 mole of helium. It's 18.9 liters. How much does 1 mole of helium weigh? Yeah, it's on the periodic table. It's like 4 something, all right? It's like 4 grams, right? So you might have thought like, oh, I have to do 3 calculations, but really you just have to do PivNerd once and recognize that it's the same volume in all of the denominators. The only value that changes in the density for each of these 3 substances is the numerator, because that mass amount is tied to the molar mass of that sample. So is this unknown sample helium? Because if you calculate it, what do you get? Do you get 2? No, you don't. All right, so this sample is not helium. Helium is a lot lighter than 2 grams per liter. So how will we get the density of argon? Mass over volume. How is this one different? Do I have to do PivNerd again? Nope, it's still over 18.9 liters, but what's on my numerator this time? It's whatever argon is. What is that? Argon is, it's like 40. So is that my unknown gas? It does look like my unknown gas. That's about 2 point something. That's argon, but let's just for completeness do xenon as well. So the density of xenon, again, is the exact same work, but the only difference is the mass in the numerator changes because the gas weighs a different amount, but the volume is exactly the same. It's still 18.9 liters, but the mass for xenon is 131.3, and so that is closer to 6.9 grams per liter. All right, so that's a lot. So it is not xenon. So what we recognize is that 1 mole of all of these gases will have different masses, but 1 mole of all of these gases have the same volume because of PivNerd. And then you just calculate that. All right, so it looks at first glance like, ooh, that's a lot of work, but it's not. All right, it looks like I did not put an answer. I just left this blank. I don't know why I did that in my key. So the next one, if you're following along in the key, number 5 is kind of another way to use the ideal gas law is, okay, we have a reaction and it produces some oxide of nitrogen. So NOx. I don't know, that X represents, I don't know how many oxygen atoms are there, right? 3, I don't know. This gas has this mass, occupies this volume at this temperature and this pressure. Let's figure out the chemical formula. So this question, I try to help you along. I ask you, what is the molar mass of this gas? It's the unit of molar mass. It is grams per mole, right? So like the molar mass of oxygen, 16 grams per mole. If I have 1 mole of oxygen, it weighs 16 grams. So if I want the molar mass of this unknown, I need the gram amount and I need the mole amount. Do I have one of those numbers already? Which one? The gram amount. So what does that mean? We're halfway done. We just need to get the mole amount. And so using the rest of the information that's here, I have a volume, a temperature, and a pressure. Is that enough information to get a mole amount? Yes, using PivNert. So PivNert, PV, nRT. I was given a pressure, a volume, R is a constant, I know temperature. I can go ahead and calculate the mole amount given this gas sample. That's my denominator. That's how I calculate molar mass. So putting it together, 0.987 atmospheres. It occupies 677 milliliters, so that's 0.677 liters. Volume, I'm solving for N, R is a constant, I don't feel like writing it down, and then 23 degrees Celsius is, I don't know, 296? Yeah, 296 Kelvin, right? I didn't do the work, so I actually have to do it. 0.987 times 0.677 divided by 0.08206 divided by 296. So I get that this gas sample, given these pressure, volume, temperature conditions, has to contain 0.0275 moles of gas, right? That many moles of gas of anything will occupy that pressure, temperature, and volume. That N amount is my denominator in the molar mass. So molar mass equals 1.268 grams. That's how much my sample weighs. And then this is how many moles of junk I have. And so that means the molar mass of this sample is something like 46.1 grams per mole. So this would be a great like numerical question on the exam. But we didn't actually fully answer this question. So yes, I have the molar mass. How can I figure out now what the chemical formula of this unknown gas is? So this is NOx. How could you figure it out? X has to be a what kind of number? It has to be a whole number. So you could just guess and check, I guess. So you can guess and check. Nitrogen is 14 grams per mole. And the rest of it has to be oxygen. So if you subtract 14, the rest of the sample has to weigh 32 grams per mole. So how many oxygen atoms does there have to be? 2. So this is NO2. You could check then, right? NO2, 14 plus 2 times 16, that's about 46. So that's a cool way we can use this application of the ideal gas law. Weigh a gas and measure its gas properties, and you can get the molar mass, and maybe that would help you calculate or determine its identity, because molar mass is tied to identity. Okay, all right, keep going. All right, let's do this one. Oxygen gas is generated by the decomposition of potassium chlorate. If 2 liters of oxygen at this temperature and pressure are collected in an apparatus with 65% recovery, how many grams of junk did we react? Percent recovery, oof. We did that in lab. Yeah, I test you on lab stuff sometimes. But here's the thing, percent recovery, it's the same as what? Percent yield. It's the same thing as percent yield. So percent recovery here is 65%. So percent yield is always actual yield over theoretical yield, right? So the information that I highlighted here, 2 liters, 27 degrees Celsius, 76 torr. This information, this measured information is what? The actual or the theoretical? Theoretical comes from stoichiometry. Yeah, so this is actual because this is what you measured in lab. right? This is what you were actually able to successfully measure. These are temperatures, pressures, and volumes that you like measured in that crappy apparatus that you used, right? So now our goal is, okay, let's measure how much gas we collect, use the percent recovery to figure out what did I need to start with to generate that with a 65% recovery, a 65% basically off here. So all this information gives us actual. All right. So, so there's a couple ways you can do it. One way you can do it is just calculate how many moles of oxygen gas you generated, figure out how many moles of oxygen gas you should have generated, and then you can use stoichiometry to relate to the reactant. So what I'm going to do is just pivnert the information given straight up. I'm just going to pivnert it right away. But this is your actual number of moles that you collected, the actual amount. So pressure is 1 atmosphere. We collected 2 liters of gas equals, I'm solving for the actual moles of gas I collected, times R, 0.08206, times temperature, what's 27? Is that 300? Yes. Wow, I'm so smart. 300 Kelvin. And so we get that the actual number of moles of O2 that I collected, so I just pivnerted it straight, is 0.0812 moles of O2. That was what was collected. And you told me this was your actual. So if we stoichiometry this number, we will get the actual amount of potassium chlorate that reacted. We want the theoretical amount. How much did we actually put into this reaction, given that 65% recovery? So I like to think about it this way, all right, 65% recovery is that we collected 0.0812 moles of O2. How much should have collected? Right? What was, if we had 100% yield, what was like the full price item? Basically, actual is like what you paid. 65% is like how much, you know, of the price you paid. What was the original price? That's how I like to think of it. So this is the theoretical number of moles that we should have collected. So should this number be a bigger number or a smaller number than 0.08? It should be bigger. We can't collect it all. So we actually we made more moles than we collected, all right? So our theoretical mole amount is 0.082 divided by 0.0821 divided by 0.65. So we actually should have collected 0.126 moles of O2. You guys are really good. If I say, okay, the theoretical moles is 100 and the percent recovery is 65%, you'll know right away, oh, 65 is the actual mole amount. But when it's the other way, when I tell you the actual and you have to calculate the theoretical, remember, that's a higher number that you had to aim for. So with 65%, you end at a lower spot, right? So this is our theoretical amount. This is the number that we use stoichiometry. So essentially we have to divide, you know, by our percent recovery to get what we should have aimed for. So at this point now it's just stoichiometry, 0.16 moles of O2. All right, so let's remember how to do stoichiometry. For every 3 moles of O2, 2 moles of the perchlorate or the potassium chlorate stuff. So where does the 3 go in my fraction? On the bottom. Yeah, so 3 moles of O2 for every 2 moles of KClO3. If I wanted a mole amount, I'd be done, but I want a gram amount. So here I give you the molar mass. Where does 122 go? On the top or the bottom? On the top, yes, because 1 mole goes on the bottom. 1 mole of that stuff weighs 122.55 grams. And then that is how much, I think 10.3 grams, you put in that container. all right? So that's your theoretical amount, but you know for a fact, I will also include 6.70 grams as a option as well. 6.70 grams is if you didn't use the 65% at all. Or I might have even gone the other way. I'll do this again. So like times 0.65 again. 4.35 grams will also be an option where you incorrectly use that 65%. You didn't scale up, you actually scaled down, all right? So scale up because we went from actual to theoretical. If I gave you theoretical and I wanted actual, then yeah, you multiply by 65%. But in this case, you divide because you want the scaled up version. How much did you aim for? Okay. All right. Okay, almost done with gases. Thank goodness. All right. All right. Concepts, no math. Okay, consider these scenarios. Which gas sample possesses the faster average speed at room temperature? Which one? Neon. Why? It's lighter. Yeah. So is that something you just memorized? Lighter things move fast. Well, sorry. Yes, it comes from the periodic table, but really it comes from the equation. The most probable speed is equal to square root 2RT over molar mass. And so you see your most probable speed goes up with temperature. Hot things move fast, but also light things move fast. So that's where the trends come from. So if we look at the molar masses, argon is what? It's like about 40, and then neon is about 20. So does that mean the most probable speed of argon is 2 times that of neon? No, it's what of neon? Root 2. It's root 2 as fast as, or the other way, sorry. Neon is root 2 faster than argon because of this relationship. Okay, yeah, so neon moves faster. Do all of the particles in a neon sample move faster than argon? All of them? No, it's just we're just comparing average speeds here, because do all particles in a gas sample all move at the same velocity? Nope, there is a distribution of molecular speeds where it shifts higher when we heat up samples, or it shifts higher for lighter particles, but there's always a distribution of speeds. Okay, which temperature will oxygen possess a faster speed? Hot or cold? Hot, yes. That on last year's exam got 100% correct. Hot things move fast. All right, which gas has a faster effusion rate? What is a fusion? It's a gas going through a pinhole. Yeah, just like this, right? So which gas will do this faster? The faster one. Yeah, that's great. That's great inference. So yes, it's the neon. The reason neon effuses faster is if you have a if you have a container, right? There's a little pinhole leak in it, and you got a bunch of gas particles. A gas will effuse as if it collides with that pinhole, exactly on where that pinhole is. So the particle that makes more collisions with the sides of the container will effuse faster. The particle that makes more collisions is the particles that are moving faster. And so that's where that relationship comes from. Collision theory is like a really big thing with statistical mechanics. We're just looking at a small glimpse of it and not that hard, but yes, that's a big thing. All right. Gases effuse faster will be neon because it's moving faster. But which one will take long? What does that mean in terms of the length it takes to effuse? Which one takes longer? This one's going to be argon. Yeah, because it's basically argon. It's going to take longer for all of the particles in here to escape this container. If argon is moving slower, it's going to take longer for it to effuse. So rate here is, I guess, inversely proportional to time it takes to do something. An example would be like, if it takes you 5 minutes to run a mile, yeah, and it takes me 10 minutes to run a mile, that's still pretty fast for me. Who's running at the faster rate? You. But then you're running at the faster rate, but it takes me longer to run that mile because I'm running at a slower rate. So that's another way to think about how time and rate are inversely Related. Okay, which gas possesses the greater density at STP? Do we have to calculate it? No, we just have to recognize that density is mass over volume. Which term is the same for both these gases? Volume, yes, because it's at the same conditions. So which one is more dense? Argon, because it's heavier. Ooh, I want to do another question. At what temperature is argon more dense? This one's going to be tough. Is it going to be 0 degrees Celsius or is it going to be 50 degrees Celsius? Which sample is argon more dense? Well, that's a great question. Maybe I should change the exam. Because in the previous one, whereas STP, 2 different samples, volume was the same. What's staying the same in this sample? Density, mass over volume. So in both of them, the mass is the same because it's argon. So the volumes are different, right? Volumes are different. So compare the volume at 0 degrees Celsius and 50 degrees Celsius. Assume that pressure stays the same. What do we think? Okay, so volume is going to be smaller at which temperature? 0 or 50? 0, yeah, so volume is smaller at 0 degrees Celsius, but it's larger at 50 degrees Celsius. So which one is it more dense? 0 degrees Celsius, yes. I like that kind of question. That was different. Okay, all right, and then finally, which gas deviates more from ideal behavior at high pressures? So at high pressure, which term is more important? The size term, so B, or A, the attractions term? At high pressure. Okay, you might just have to memorize it, all right? So the B term, the size term, is more important at high pressures, or when you see like small volumes, those kind of go hand in hand with one another, all right? The A term, attractions, is really important at low temperatures. I like to think of it this way. Attractions are important. We just learned about attractions, right? When your particles are moving really fast and they're slightly attracted to one another, they'll just be a little bit sticky. Every time they have a collision, they'll just stick to one another a little bit and lose a little bit of kinetic energy. That's called an inelastic collision. But that little loss when the particles are already moving really fast is really small, right? That little bit of loss. So if attractions are happening and the particles are already moving fast, there's not much difference between the ideal gas equation and then versus the real gas equation. Versus if your particles are cold and they're already moving slow and they're slightly sticky on one another and they lose a little bit of their kinetic energy via attractions, we see that the amount of loss when they're already moving slow is a lot more significant. And so that's why at low temperature, attractions are really important, because the ideal gas law ignores attractions. But at low temperature, we can't ignore it because those attractions do change the extent of the kinetic energy that is available for your sample, because there's just not a lot of kinetic energy to go around, right? So then your B term is more important at high pressures, because in order to make a high pressure, you need to shove a bunch of particles in a container. And so if you're shoving lots of moles of gas in a container, those gas particles actually take up space. And so the size of the particles tend to matter at those high pressures or at very small volumes. You're shoving a lot of particles in a small volume. So what do we care about here at high pressure, the A term or the B term? The B term. So which one deviates more? The heavier one, so argon. Yes, argon has the bigger B term. That's basically what I'm asking, but you had to figure out, oh, she's asking about the B term, so I just need to look at size. All right, finally. All right. A 1 mole gas sample at STP has a predicted volume of 22.4 liters. That's using the ideal gas law. That's just PIV nerding, 1 mole, 1 ATM, 0 degrees Celsius. But if we considered a gas to be a real sample, what should we predict about 1 mole of gas at 77 Kelvin, so really cold, at 1 atmosphere? What do we think? What term is important here at 77 K? Is it going to be the B term this time? Nope, it's going to be the attractions term, yeah. So what do we think? Will the actual, if the A term is important at 77 K, what will our actual volume be? Will it be smaller than, yes, smaller than predicted or larger than predicted? So I like to apply, okay, turn on attractions. If particles are attracted to one another in a gas sample, that whole gas sample will contract because now the particles are more attracted to one another than the sides of the container. So the actual measured volume of the sample is going to be less than what the ideal gas law predicts. I think that's the answer, right? It's not going to be more, and it's not going to be the same. If we were at ideal conditions, then it might be the same, but we're not. This is at a very, very low temperature. For completeness, when is the ideal gas law really good? When? At what conditions? I like to just remember Earth. Earth is what? Low pressure, but high temperature. Those are when the ideal gas law works really well. Low pressure means the B term, unimportant. High temperature means A term, unimportant. So that's why the ideal gas law works at those conditions, at earthly temperatures or conditions. Thank goodness we live on Earth. All right, so let's keep going. Okay, page, 3. All right. Let's go into the pits of it. All right, so electronic structure. We talked about light, why light is important with us understanding electrons, and all of that. So monochromatic light source delivers 227 kilojoules per mole of photons. What is the wavelength in light in nanometers? So you have an equation on your sheet, E equals H nu or E equals HC over lambda. So since I want wavelength, I probably want to use this equation, the second one. All right, so E equals HC over lambda, but that energy is the energy of what? 1 photon. 1 photon. Did I give you the energy of 1 photon? No, I didn't. I gave you the energy of a mole's worth of photons. But when I gave this question in 1210, it did so poorly. Because so many students just wanted to stick 227 into this equation and just be done with it, right? But we have to convert this per mole value into the energy of just 1 photon. I'm telling you the price of a dozen eggs. I want you to calculate before you put into this equation, what is the price of just 1 egg before you put it in, right? So we just have to scale this down. So the best way to do this, I just look at the unit. So 227 kilojoules per 1 mole of photons. I need to convert that into, okay, 1 mole is 6.022 times 10 to the 23 photons. But before I am finished, I'm gonna convert that kilojoule into a joule amount. And so you get that 1 photon, just one egg costs 3.77 times 10 to the negative 19 joules is 1 photon, just 1. And that is E in this equation. So E, let me move this over here. All right, 1 photon has that energy. So that is equal to HC over lambda. So H is a constant that I give you. Do note where it is on the supplemental information sheet, so you don't have to spend time looking for where it is. And also spend time, if you have a calculator, look for your E button, your exponential key, or if you're going to use the calculator on the on Respondus, look at the test browser and see where that E button is, because I think during the exam someone asked me where is that button, because they were just using the thing and I couldn't find it, but it is there. I did find it eventually, but you don't want to waste time doing that. Okay. So 6.626 times 10 to the negative 34 joule second. Speed of light is 3 times 10 to the 8 meters per second. Solve for wavelength. You solve for wavelength. What's the unit that pops out? Meters. Meters, because speed of light is in meters. And so this wavelength is 5.27 times 10 to the negative 7 meters. And so if we convert that to nanometers, so 1 times 10 to the negative 9 meters is 1 nanometer. This is 527 nanometers. So that is right in the blue region. Sorry, no, green. It's green. Okay, all right. So that's a plug and chug. All right, let's look at this diagram and select the incorrect one. Oh wait, yeah, the incorrect one. Okay, so we have 3 waves and we have 3 transitions. Match the waves with the let's just match the waves with the transitions. All right, so these waves, let's rank them on terms of energy. Why do I want to rank them in terms of energy? What's the point of that? It's because these transitions, A, B, C, their magnitudes relate to energy, right? Because these are energy levels. So when an electron falls from 2 to 1, that energy difference is related to the energy of the photon that's emitted or absorbed if we go up the ladder. So which wavelength is the most energetic? 3, yes. Most energy, because it has the shortest wavelength, versus 1 is the least energetic because it has the longest wavelength, and then 2 is in the middle. All right, so which of these waves is A? 1, 2, or 3? It is 3, yes, so A. And then what about which wave is, which transition relates to the low energy wave? This would be C, and then B would be the middle. And so we see here that the largest transition is between 1 and 2, because if we think about the spacing, you're going to have the largest space between 1 and 2. Energy letters, these rungs on the ladder aren't very good. They get closer and closer the further you get up. So the largest step is between 1 and 2. Then it gets smaller between 2 and 3, then even smaller with 2 and or 3 and 4, and then so forth. So it looks like this. All right. All right, so which one's wrong? Is it C? Wait. Wave 1 should be A. Yeah, that one's wrong, because A is high energy, so this should be short wavelength. That's what we want. So C is the answer because it's the incorrect one. Okay, all right, keep going. All right, here's another way I can ask it. Select the electronic transition that results in the emission of a photon with the longest wavelength. I love these because there's a billion ways I can ask them. So the first thing is start with an appropriately spaced electron diagram. If you make them all evenly spaced, you cannot answer this question. It has to be appropriately spaced. So I just need one more between 4 and 5. So if this is emission, if light is being emitted, how is the electron moving? Is it going up the ladder or down? Yep, it is falling. So you're looking for an electron falling. Longest wavelength means what in terms of energy? Small energy. So we are looking for a small fall, little fall. So let's just do process of elimination. We only want the emission one. So 5 to 1, is that a fall? Yeah, so that one's emission. 5 to 4, that's also emission, but 4 to 5, that's absorption. So we can eliminate that one right off the bat. 1 to 5, also absorption, because that's a jump. And then 2 to 1, that one's emission. So we're looking for the smallest fall. So 5 to 1, 5 to 4, and then 2 to 1. So quite obviously you can see that it's 5 to 4 is the smallest fall, but let me just prove it to you. If you don't draw it correctly, if you draw it like this, can you distinguish between 5 and 4 and 2 and 1? You cannot. If you don't draw it correctly, you cannot answer this question. So that important piece is not just, oh, looking for the smallest fall, but also how the energy levels change as you go higher and higher up, right? They get closer together. All right. All right. Which statement about de Broglie is false? Which equation on this supplemental is about de Broglie? What did de Broglie do? What did he get his Nobel Prize in? The wavelength. Yes, the de Broglie wavelength. So if we go back to the supplemental thing, here's supplemental. Here. The equation under E photon, wavelength equals H, so Planck's constant over mass times velocity. De Broglie said everything has a wavelength. Every object in motion has a wavelength. If I walk across this room, I have a wavelength because I have a mass and I have a velocity. Electrons, they have a wavelength. Do electrons have mass? They do. Remember the little experiment I did with the little spinning pinwheel? Yeah, they have mass. Do they have velocity? Yeah, they're spinning around like crazy idiots. So they have a de Broglie wavelength. So let's go back to there and think about that. So let me just write that equation because that's what's going to help us. It's wavelength, the de Broglie wavelength equals hmv. I'll point out that we have two equations that have wavelength in it. E equals hc over lambda, wavelength equals h over mc. Get them, they're different. This energy wavelength equation describes a photon. A photon is another word for what? Light. Light. But the de Broglie wavelength equation, do we use that for photons? Do photons have mass? No. So we use this for electrons or objects in motion generally. So these are the two equations that have wavelength in them, but keep them separate. It'll help you out here. Okay, so which are false? All matter possesses a wavelength. Is that true or false? True, because all matter has mass. And doesn't that equation say anything that has mass has a wavelength? Yeah. The de Broglie wavelength of an electron is longer than that of a proton. So how do the de Broglie wavelengths differ here? So it's going to be the masses. So an electron has a mass that's a lot smaller. So how will its de Broglie wavelength be different than a proton? It's going to be longer. Yeah, because an electron, real small, a proton is real massive. It has a really, in comparison, a very large mass. So that means protons have what? Long or very short de Broglie wavelengths? Very short, very, very short, because their masses are so big. If you have a big number in your denominator, wavelength is a small number. So that one is what, true? Yes, it's true. Okay, the de Broglie model of the atom is based on the idea of standing waves. That is true also. De Broglie talked about waves. So instead of the electron just orbiting, you know, like a planet, right, in our solar system, he just said, oh, that electron, instead of orbiting, spherically, that electron has a wavelength that encompasses each of those orbits around our nucleus. So that one is true as well. And then the last one, larger the object, longer the de Broglie wavelength. So large object mean mass big. So that means de Broglie wavelength small. So that one is the false one. So it's just navigating that equation versus actually calculating it. Okay, let's consider two different orbitals and select the false statement. So I have a 3p orbital and a 4p orbital. Let's look at the first one. A 3p orbital must have the same angular quantum number L as a 4p orbital. That is true. Why don't we just go through the quantum numbers? So 3p and 4p, what are the n values for each of these respective subshells? For 3p, what is n? Don't think about it too hard. It is 3. Where did I get that? It's the 3. What about the 4p? What is its n? 4, perfect. What about L for each of these? 3p is 1, and 4p is also 1. Yeah, so remember our L values, they have numbers, so 0, 1, 2, 3, etc. But these also relate to shapes. So 0 is our S, P, D, and then F. Where that L quantum number, it's how many angular nodes each of those shapes have, or it's how many times you twist the balloon animal to get that shape. To get us, if you have a balloon and you twist it 0 times, you're still left with a spherical balloon. But if you twist a balloon once, you get a dumbbell. That's what a p orbital looks like, and so forth. So 3p, that is true. 4p is a higher energy level than 3p. What quantum number compares energy? The n value. The n value is no different than these n values. See, 1, 2, 3, 4, 5, 6, whatever. Right? So n equals 3 is here, n equals 4 is there. So 4 is definitely a higher energy. So there we go, true. 3p must have the same orientation as 4p, true or false? That one is false, because did these indicate any orientations? Orientation is our m sub L quantum number, yes. So I only gave you n and L. The possible m sub L's are the 3 that we're allowed to have inside a p subshell. So +1, -1, or sorry, +1, 0, -1 for each of these. So technically, I didn't tell you where the electron is. You could put an electron here in one of the orbitals and in 0 in the other one, and those are still valid quantum numbers. So that one is the false one, but let's just do the all for completeness. So a 2p orbital has the same number of lobes as a 4p. That is true. Both of them look like dumbbells. Just one of them's bigger. All right. They both look like p orbitals. Okay, keep going. Yeah, all right. All right. Okay. I don't want to do this question, so I'm gonna write a new question. Okay, I'm gonna give you a set of quantum numbers, and you're gonna tell me if it's allowed. Am I allowed to have that? Try to write it. What orbital is this? So I say n equals 4, L is 0. So what shape is that? S. So what is this? That's a 4s orbital, okay? It's a 4s orbital. Is this orientation allowed for an s orbital? How many boxes are in a 4s orbital? Just one box. That one box has a orientation of 0. That's it. So that is also allowed. What does a +1/2 mean? Spin up, boom. Is that allowed? Yes, this is a valid set of quantum numbers. Okay, let's do another one. What if I do 3, 2, +3, +1/2? Is that allowed? No, where is it not allowed? The m sub L, yeah. So for funsies, for the first two, what orbital is this? Or sorry, what subshell is this? 3D, because L of 2 is a D. So how many boxes are in this subshell? In a D subshell? There are 5. 1, 2, 3, 4, 5. Because how many electrons can fit in a D subshell? 10. 5 boxes, 10 electrons, 2 electrons in every box. And so if we label these orientations, 0's in the middle, -1, -2, +1, +2, you can clearly see there is no room for a +3. So that's why that one's wrong, right? That's why these rules are here. Okay, let's do another one. So that one's not allowed. What if we did 3, 3, 0, +1/2? Is that allowed? No, that is not allowed, because what are the rules with L values? They have to be, the possible ones are only n-1. It doesn't mean that you have to do n-1, all right? The possible L values we can have, 3 is not one of them. We can have an L equals 0, 1, or 2. So that means what can exist for an n equals 3 subshell is a 3s, 3p, or 3d. Either of those are valid, right? But a 3 L of 3, so an F, a 3F does not exist. So this is also not valid. Okay, let's do another one. What if I had 5, 4, 0, plus 1/2? Is that allowed? Not allowed. Okay, so let's just go through this. L of 0, 1, 2, 3, 4. So let's just go through the shapes. 0 is S, 1 is P, then D, so S, P, D, F, and then you just go alphabetically, so F, G. So this is a what kind of subshell? 5, G. Weird. Okay, but no matter. Okay, so what are if we have an L of 4? How many different orientations can we have? See if you can't see if there's a trend. S orbitals only have 1 orientation. P orbitals have 3. D have 5. F have 7. So G needs to have 9, right? Because the number of boxes is all of the integers between -L and +L and 0 in between. So the possible things are going to be -4, -3, -2, -1, 0, +1, +2, +3, +4. So there has to be a box for each and every one of those. So I'm saying, oh, you're putting an electron right there. And is that allowed? Yeah, it is. Okay. Do you want to do another one? Are we good? Meh? No? Yeah. You figured it out? Okay, yes, yes, perfect. Okay, so if I told you we have a 4F orbital, tell me what are the quantum numbers? N is 4, and then L is 3, perfect. And then what are my possible M sub L's I can have? -3 all the way to +3, perfect. Okay, all right, I'm gonna skip those. I'm gonna skip those ones too. Because I know it's on the exam, so. All right, tin has 50 electrons. Which electron experiences the highest effective nuclear charge? Do we have an equation for that on our sheet? Yeah, what's the equation? F equals Z minus F. Oh, that sucks. That's not very helpful. Unless you know how to use it. Z implies what? It's how many protons are on the atom. So since I'm inspecting a tin atom, this is what? 50 protons are in my tin atom. So what I like to think of is, okay, I have a tin nucleus, right? There is my stage. Here are all my electrons, right? Those energy levels are like rows, right? All these folks in the splash zone, if I'm +50, you feel what? Positive charge, +50, but you right behind them, see, there's 3 electrons in front of you, so they're obscuring my full 50 charge. So your shielding is 3. There's 3 electrons in front of you. So you feel a Z effective of 47 because you have 3 shielding. So of these electrons, we need to determine what's the shielding in all of them. So the shielding aspect is all the electrons in lower N values. That's what we're looking for. All right, that's how you calculate shielding for any substance. But mathematically, which electrons will experience the highest effective nuclear charge? Just go to a concert. Do you want to sit in the front row or do you want to sit in the back? You want to sit in the front. You want to sit in the front because your shielding is small. There's not a lot of folks, there's not a lot of electrons in front of you. But if you're sitting in the back row, all of these electrons, they're in front of you. All right? So all the folks that are sitting up in the balcony or in the back row, you're experiencing a different experience in lecture versus the folks in the splash zone. Okay, so what's the answer? Which electron? So really, you don't have to calculate a dang thing. Which electrons experience the highest effective nuclear charge? It is the 3s. Yeah, it's the 3s electrons because they're sitting in the third row versus all of these electrons, they're sitting in the back rows. They're being shielded more. I don't have to calculate anything, but I can if I want. Yeah. D block, it gets weird. But here's how you do it, all right? So here it is, right? Here's a periodic table. So let's do tin. Oh yeah, tin. So remember the trick with effective nuclear charge for valence electrons? What's the tip? What's the trick? It's always the group number. That's it, all right? So for main group elements, all of these elements, they have a Z effective of +1 in their valence shell. These electrons, or these elements, +2 in their valence shell. Fluorine, since they're group 7, all of those elements have valence electrons that experience +7, right? So that means tin should have a Z effective of +4. So how the heck do you get that? So let's write out, let's not be lazy, let's write out the full not full electron, let's just do shorthand. So let's be a little bit lazy. Krypton. Then we're at rubidium. So what subshell is that? It's an S, but which one? 5. Yes, 1, 2, 3, 4, 5. So 5s, 2 electrons. Then yttrium starts what? 4d. And how many? 10. And then 5p, 2 of them. So we want to inspect the valence electrons. So we are sitting in the 5th row. So that means we count when we do, Z effective, okay, Z effective is Z minus S. When we calculate S, we want to count all of the electrons in n equals 1 through n equals 4. All of them, all of them. So krypton takes care of how many of those electrons? 36. Do I count these 4d electrons? Yeah, they're in the 4th row too. They're in that, like, you know, valence shell kind of written on the outside, but we're not counting them towards the valence shell count. This is actually in our inner shell. It is. So the shielding for tin in this example, not zinc, tin, is actually 46. It's 46. So let's do the full thing. So for tin, all right? Your Z effective is your Z. What is Z for tin? +50. There's 50 protons in your center stage, and we are subtracting 46 inner electrons sitting in rows 1 through 4, and you're in the nosebleed seats in row 5. And so we get, those outer nosebleed electrons, they're only attracted +4. Is that consistent with our trick? It is, but it's weird because we have to include these ones on the outside. Usually we don't. So like, for example, if we did magnesium is just neon 3s2. So here for magnesium, Z is +12, but we're subtracting what is our shielding? Just is coming from neon, so it's 10, so it's +2. So here there's no like weird things on the outside, we just consider the noble gas, but once things get heavier, we actually have to start considering the D block. But to answer this question, again, we don't really have to calculate all of them, but we could if we wanted to. Okay, keep going. All right, so my favorite. These questions should be easy ones. Which are larger? Which has the higher ionization energy? Which is the more favorable electron affinity? Because all of them trend with size. So if you're good with size, then hopefully you're good. So choose the larger atom and tell me why. Here, these are the factors: N, Z effective, or electron repulsion. So look at N first. If two elements are in the same N, then go to Z effective. If things look weird and they're charged, consider either isoelectronic things or Z effective or number of protons in your nucleus. So tell me, which one's larger, iron 2+ or 3+? Why? It has more electrons, yes. O2- or sodium plus, which one's larger? That's weird. But if you look closely, they both have the same number of electrons. Those are isoelectronic. Both of them have 10 electrons each. But how do those atoms differ? Yes, their N values differ. They do. But yeah, so you might say, oh yeah, sodium is at N = 3, but oxygen's at N = 2, so sodium's larger. But that's actually not true. So if we would have just done Na and O, neutral, yes, sodium is bigger. But once we start making them ions, it's different. So this is an example of a weird isoelectronic exception. Both of these have 10 electrons. Oxygen, though, has 8 protons, and sodium has 11 protons. So you have an atom with these things in it. 10 electrons, 8 protons. Or this atom, 10 electrons, 11 protons. Which one is larger? Oxygen. So here, this one's larger because those 8 protons pull in those 10 electrons more loosely because they're just not attracted to it as much, all right? I'm a dumb electron and I'm more attracted to a +11. And so I'm gonna sit closer in the sodium plus versus the oxygen atom, all right? So in this one, yeah, oxygen's bigger. Sorry. Yeah, all right, next one. What's this last one? Potassium or bromine? Which one's bigger? Potassium, yes, but that's weird. Isn't that weird? Because potassium's so much lighter, right? The molar mass is so much lighter, but again, it's because of Z effective. Potassium, its valence electrons are just attracted +1, but bromine is +7. And I always think, if I'm a dumb electron, where am I gonna go? Bromine, I'm gonna sit closer on a bromine atom because it's a higher effective nuclear charge. All right, so I think those are the answers. Okay, keep going. So which of the ions possess the larger ionization energy? So what's the trend here? Ionization energy is energy to remove an electron. So an electron is going to be harder to remove if it's closer, if the ion is smaller. If your dragon is hoarding all of the electrons under its wings, real hard to snatch one of them electrons. But if your electrons are just floating off very far away from your nucleus, very easy to take one off, right? So what are we really looking for here? Which one is smaller? Yeah, that's essentially the question you're answering, okay. Potassium or bromine, which one is harder to remove an electron? Bromine. Your electrons are attracted +1 on potassium, but +7 on bromine. It's harder to remove from a +7. It's more attracted. All right, calcium or calcium plus? Which one? Plus, yes, that one is harder. A lot of folks will think, oh, but calcium wants to be a 2+. No. It's all about energy. It's all about electrostatics. Calcium 2+ is smaller. It will always be harder to take from the smaller thing. All right, chlorine or chlorine minus? Which one's harder? Neutral or anion? Neutral, yes, because it's smaller. Phosphorus or arsenic? Phosphorus, why? Because it's smaller, but for what reason? N, perfect. All right, keep going. All right, so which one gives the most negative electron affinity? Meaning you put an electron on, in which case do you get more energy out? So the trend is you get more energy out when the electron you place is close and attracted to your nucleus. So you will get the most energy out when you place an electron on something that is already small. So we are just looking for what is small, the smaller thing. So iodine or bromine, in which one will you get more energy back? Bromine, why? Because it's smaller, I know, but like for what reason? Yes, N. Aluminum or phosphorus, which one will you get more energy back? Yes, phosphorus, because it is smaller. Because of what? Z effective. Yes, aluminum is +3, phosphorus is +5. Your dumb electron, where are you more attracted to? +5. Okay. Chlorine or chlorine plus? Plus, why? It's smaller. Also, remember, electrons, they're negatively charged. Yes, this chlorine has a +7 Z effective, but this chlorine has a +Z effective and it's already positively charged. There's a lot of attractions right here because this chlorine plus is already positively charged. Okay, last one, chlorine or chlorine minus? Just regular chlorine, yes, that one. Okay, there's more attraction here. There's a positive Z effective. This attraction here actually isn't attractions, chlorine minus and an electron. Those are two negative things. That sounds like repulsion to me, and that is not favorable. You actually have to put energy into the system to make this happen. Great. Okay, so those are great questions. Hopefully those are, low-hanging fruit questions you can just zip through. Okay, keep going. All right, which figure shows the ionization energy for aluminum? So this is successive ionizations. So I'm taking electrons off one at a time. So you are looking for the graph that has what kind of feature? Three small peaks. So is it C? But C has 3 small peaks. But what's wrong with C? That third one is screwed up, right? You cannot have a third ionization energy that is easy. It can't be easier to take the third electron off than the second one, because aluminum will always get smaller as we take more electrons off. So it's D, it's not C. Okay, what is the third ionization, the equation? What is the equation for this messed up one? That energy represents what equation? The third ionization energy of aluminum. So we're taking off the third electron. So what's my reactant? Aluminum. Is it just aluminum? And then we rip off 3 electrons to make aluminum 3+? No, you got to take them off one at a time. So if we write them all out, maybe that'll help you. The first ionization energy is aluminum plus, and an electron. The second ionization, what's my reactant? Aluminum plus. So we start with the reactant is the product from the previous one. And so now the product I make is aluminum 2+ and an electron. So I ripped that second one off. So my third ionization energy is actually aluminum 2+. That's what I start with. There is my third electron I ripped off. So that is the third ionization energy. Okay, so then what is the second electron affinity of oxygen? The second electron affinity, what would be the equation for that? What's my reactant? O plus? Electron affinity, am I ripping off electrons? I'm adding electrons, so you're adding the second electron. So my reactant is O minus. I add an electron, O2 minus. That is my second electron affinity. Right? The first okay, I'll write the first one. The first electron affinity of O is O plus an electron, gives me O minus. And so see how I take the product in the previous one, make it the reactant in the next one. There we go. So just write all of them. Okay, finally, the last chapter. My favorite. Without using any tables, just use trends. Rank these bonds in increasing polarity. So polarity is proportional to the difference in electronegativities of the two atoms involved in your bond. So if you have two atoms that are really far away from each other on this periodic table, that's going to be a superpolar bond. Cesium, not polar at all. It's not electronegative at all. Fluorine, super electronegative. So when you take the difference, that's going to be a huge number. That's a straight up ionic bond. But unfortunately, those are not the examples I give here. So I have a O-N bond, a N-F bond, and a S-F bond. Okay, tricky, tricky, tricky. So, O, N, and F. Compare those electronegativities. Those three elements, they're all part of, what do I call it? The high five. The high five, what does that mean? They all have very high electronegativities. They're all very high numbers. So if you subtract a large number from a large number, what kind of number do you get? A small number. So will you make a polar bond with two very electronegative things? No, you don't. What you want is a mismatch. Mismatches make really great polar bonds, but when they're both high, it's not going to be super polar. So if you look at O and N, they're right next to each other on the periodic table, and they're both really polar. So delta En is going to be what kind of number? Really small. Okay, what about N and F? N and F are both also really polar, but can we make a comparison to N and O here? When we look at the bond between N and F, it's going to have a small delta En, but is it going to be bigger or smaller than N and O? It's going to be bigger, yeah. So it's going to be larger than N and O. And the reason is because N is staying constant, but F is more electronegative than O. So we're going to see that difference increase as we kind of move further away from each other on the periodic table. Okay, perfect. So NO is the smallest, least polar at this point. NF is more polar, but how does SF compare to these? Is it going to be more polar, less polar? What do we think? More. Why is it more? Sulfur is not electronegative. It's not part of the high five. So that automatically makes SF the most polar bond. So we can figure this out all without electronegativities. So most polar is SF, and then ON is the least polar, and then NF is in the middle. Perfect. Right, and we got that all from the periodic table. If you're good with the high five and recognize two elements in the high five will always make a not so polar bond because both of them are high numbers, then you'll be good. And then everything else is a not high five. I think another one I like to do, because if you recognize, like if I do C and N, all right, like a CN bond, its polarity versus a CO bond, that polarity, CF bond, that polarity. We see the further we get, like the further the two elements are on the periodic table, the more polar the bond is, right? But in that case, C is staying constant for both of those. But here's another one that I like to do. What if I do OCl? I think this is a fun one. OCl or NS. Which bond is more polar? Why NS? But they're both the same. They're both like just diagonal away from one another. Why is NS more polar? Yeah, oxygen and chlorine are part of the high five. So that difference is gonna be smaller. Sulfur, not so electronegative, but nitrogen, very electronegative, so you're gonna get a larger difference there. Perfect, good. So you just think our way out of it. We don't have to memorize things. Don't memorize things. Your brain, save your brain space for other things. Okay, how many more do we have to do? Gosh, there's a lot. Okay, let's do, Okay, yeah, let's do this one. Complete the Lewis structure. So all atoms obey the octet rule. How many lone pairs are on this thing? So the octet rule says when you draw Lewis dot structures for like hydrogen, carbon, nitrogen, what's next? Oxygen, and fluorine, these Lewis dot structures tell you how many bonds each of these needs to make and how many lone pairs are in each. So each of these lone dots on these dot structures, hydrogen tends to make almost always one bond, and that's it. Carbon, on the other hand, always makes how many bonds? 4. Nitrogen, 3, because it already has one lone pair. Oxygen will always make 2 bonds total because it has 2 lone pairs. And then fluorine only ever makes 1 bond because it already has 3 lone pairs and it has 1 of those unpaired things. So when we draw a skeleton structure, we just need to use these ideas to complete it. Make sure everything has the right number of lone pairs, right number of bonds to complete octets. So I want to draw this. So all of the nitrogen, carbons, and oxygens, they're connected to one another. So we have an N, C, 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 O chain. Now I want to just connect the hydrogens to each atom and make sure that there's the appropriate number of them. So this first nitrogen, I'm reading left to right, has how many hydrogens attached to it based upon its structure? Just 2, so 1, 2. All right, the next carbon just has 1 hydrogen. The next carbon only has 1 hydrogen. The next one has 2 hydrogens. And then that oxygen has just 1 hydrogen. So we need to figure out how we can complete this Lewis structure. We're going to use this as our guide. So I'm going to just fill in lone pairs because I know that those do not react. This nitrogen needs a lone pair. What other atom needs a lone pair? Oxygen. How many? 2. So 1, 2, 1, 2. So let's check off and see if things have complete octets. How about the hydrogens? Do we have to do anything to the hydrogens? No, we place them, that we're good. This nitrogen has a complete octet. It has 3 bonds and a lone pair. That oxygen, 2 bonds, 2 lone pairs. What about this carbon? Is that one good? Yep. But what about these 2 carbons? Are they good? No. So should I just add more electrons like this? No, that's not what the octet rule says. It says that carbon will always make 4 bonds. So the easiest way to do that is put a double bond between them. So now you've shared electrons, 1, 2, 3, 4 bonds on this carbon, 1, 2, 3, 4 bonds on this carbon. And so we see that this structure has 3 lone pairs total, and then I guess, 1 double bond. That's another thing I could ask as well, or maybe even both, I don't know, in one question, right? And so that's not obvious in this kind of line diagram that I showed. Okay, yeah, all right, let's do this one. These are 2 Lewis structures. What's the most dominant structure? So we need to consider formal charges. When I say dominant, I typically mean, hey, both of these structures, if you look closely, they satisfy the octet, both of them. I'm pretty sure. Yes, they do. But one of them is more dominant. One of them is more correct. Both of them have complete octets. We follow the octet rule. It's just one of them's more correct than the other. So how do we calculate formal charge? Once minus has. So once comes from the periodic table, has comes from the Lewis structure. So once minus has. Oxygen wants how many electrons on it? From the periodic table, 6. Nitrogen wants, that's 5, yeah. Chlorine wants 7, and then it's 6, 5, 7 again for these things, right? That's from the periodic table. That's the number of valence electrons on all these atoms. Now let's look at the structure and count, well, how many electrons does that atom actually have in the structure? So oxygen has 1, 2, 3, 4 coming from lone pairs, but we're splitting up the electrons in bonds so they go to each of the respective atoms. So that double bond, 2 of them go to oxygen, 2 of them go to nitrogen. So it's like an equal split divorce of all of the bonds. The single bond on the other side, chlorine gets 1 of them and nitrogen gets the other. So this oxygen has 6 electrons on it. The middle nitrogen has how many? 5. The last chlorine has 7. Perfect. So you add those up. Ooh, look, nice. See, all zeros. All right. So then let's like this one. Why don't we put the double bond on the other side? Formal charge, or sorry, how many electrons on this oxygen? 7, because 1 from that bond. Nitrogen still has 5, but chlorine has 6. So you add those up or subtract them and you get this oxygen has a -1 formal charge, nitrogen has 0, and then chlorine has a +1. So which one is preferred? A. And for what reason? It minimizes formal charges. All right, 0 is preferred. But if you have to have a formal charge, you want to put it on the most electronegative atom. So let me give you an example. If I did this again, all right, if I had like O, N, and Cl or something, O, N, Cl, pretend that I actually have a structure, and I told you that these formal charges are, oh wait, I don't want to do O. Okay, we'll do this. We're gonna just make up some compound. Yeah, okay, we're gonna just make up some compound. What if I told you the formal charges on these were 0 on the carbon, 0 on the nitrogen, -1 on the chlorine, or -1 on the nitrogen, 0 on the carbon, 0 on the chlorine? Which one is the most dominant Lewis structure? Does one of them minimize formal charges more than the other? No, they're equivalent. So what's the next line of defense that we look at? Where that negative is. The negative wants to be where? On the more electronegative atom. So if we have a choice, we want to put that negative charge on which atom? The Cl. So in this case, it would be compound, this Lewis. I know it's not complete. I just wanted to put the charges on different atoms. And so yes, we see, oh yeah, that -1 charge will be much better suited on a chlorine atom versus a nitrogen atom because of electronegativities. Okay, all right, so that's another way we could do it. Okay, all right. I don't want to do this one. Let's do this one. Let's do this one. Consider this Lewis structure. Order the labeled bond angles from smallest to greatest. Okay, we want to consider deviations. So our strategy here is you need to first determine the electron domain. Okay, so we want to get the electron domain of the central atom in the bond angle, right? You want to predict the ideal bond angle for that specific domain. Usually these are going to be like trigonal planar or tetrahedral or something like that. Then you want to consider deviations that may happen. Deviations that either come from lone pairs of electrons or from double bonds. That's the order. So let's go through these. This carbon has what electron domain? What's the number? 4. What does 4 mean? Tetrahedral. What is an ideal bond angle on a tetrahedral? 109.5. Is this bond angle going to be 109.5? Yes, it will. There are no deviations. There's just single bonds all around this carbon atom. I know that this is a big molecule, but just look at every atom as its own central atom. And so in bond 1, this carbon atom is the central atom. So this bond 1 is going to be really close to 109.5. Okay, so let's do bond 4. So bond 4 has how many electron domains around this oxygen now? Because that's like the central thing. has 4. So 4 is what shape? TD. So what's the ideal angle on TD? 109.5. But will bond 4 be exactly 109.5? Is there any deviations that occur on that central atom? Is there anything that screws up our angles? Those lone pairs, they're going to screw it up. They're going to do what to those bond angles? Bring them closer together, because those lone pairs, what do I say? They're big, fat, and juicy, and they just take up more space, and they're going to push together those other bonds together. So 4 is going to be slightly less than 109.5. Cool. So now we gauged between 1 and 4. Okay, let's do 3 and 2. So 3 and 2, interesting. They both actually share the same central atom. What is the electron domain on those bonds? 3. 3 is equal to what shape? Trigonal planar. So what's the ideal bond angle on a trigonal planar? 120. So now we need to decide, how does bond 2 and 3 adapt to any deviations with 120? What might be easier is if you draw this, because right now it looks T-shaped. This is not T-shaped, it's trigonal planar. So we have a carbon that's trigonal planar, but one of those bonds is a double bond. So if we draw what indicated bond angles I'm trying to get you to look at, this is bond 3, and then this is bond 2. So what kind of deviations are we going to see? Bond 3 is going to be what compared to 120? It's going to be less, yeah, because that double bond is going to squeeze and push all of those other bonds closer together. So bond 2 is going to be greater than 120 degrees, all right? So, I mean, if I let me just make up numbers to help you along. That double bond takes up more space generally. And so these two bond angles, these red ones, they're gonna just be slightly more than 120 degrees. So let's say they're like 122 degrees. Okay, they're just slightly expanded. They take up a little bit more room because that lone pair is big and fat and puffy. So based upon what I think I know about angles and geometry and circles, what's this missing piece have to be to make a true circle? Is it gonna be 120? No, it's gonna be, I think, what is that? 116 or something like that. So these numbers make sense now. See how that angle that's directly adjacent, directly across from that double bond is now slightly smaller, while these two adjacent bond angles are slightly bigger, all right? And so that is the strategy. So let's actually answer the question. Smallest angles are going to be the tetrahedral ones, okay, because they're in the 109 regime. So which one's smallest? Bond 4. Bond 4 is smallest, then it's 1, because here it's less than 109. Here it's exactly 109. Then what bond angle is next? 2 or 3? It is 3, because this one is less than 120, and then 4 is greater than 120. That's a tough question. Yeah. Are you making angles with your hands? Oh, it's 2? Yeah, okay, sure. Yeah, bond 2. Good. All right. Okay, we have 15 minutes. Is there a certain question you want me to go over? What number? Just keep going. Let's do... Okay, let's do... how are you with 6 steps? Eh? You want to do them? That's all, what? Nothing? Okay. Yeah, okay, let's just do the 6 steps. All right, let's draw these suckers. I'm sick of the 6 steps, so But hopefully at this point you've drawn BF3 enough that you know it's just 3 single bonds. I hope. All right, okay, so what are the 6 steps? Count valence electrons, that's step 1. So the valence electron counts for all of these. So we have 5 plus 4 minus 1 for NH4 plus. It's minus 1 because it's a cation. I think that adds up to 8. PCl4, oh, I guess I have a key. It's 5 plus 3 times 7. What is that, 26? I'm just doing all of them at the same time. Xenon F2, so that is 8 plus 2 times 7, so 22, thank you. BF3, 21 plus 3 is 24. So those are the electrons I have to spend. So for all of these, we make the skeleton structure. So let's do NH4 first, NH4 plus. We draw nitrogen in the middle, single bonds to all those hydrogens. How many electrons have I placed? 8. So do I place any more? Nope, we're good. So you just put them brackets on and you're good to go. That's it. Check, everything has a satisfied octet. We're good. Okay, PCl4, or sorry, 3. So phosphorus in the middle, 2, 3 chlorines, boom, boom, boom. I've placed 6 electrons. I still have more electrons to spare. Where do I put them? Outside, then inside. So 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And then the last 2 go on the center. If you don't count properly, you will not get the correct number of electrons on that central atom. You got to count carefully. All right, so there's PCl4. Everything has a satisfied octet. We're good to go. All right, next one is xenon F2. So we put xenon, 2 bonds to fluorines. We've placed 4 electrons so far. We have 22 to spend. So 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So I'm going to place 6 more electrons on xenon. Count super carefully. Do not just spray and pray and like stop whenever you feel like it. There is a strategy, and if you follow my 6 steps, you will always be right. Do you want to always be right? Yes. So follow my 6 steps. So there is that one. That one, fluorines have satisfied octets, but xenon has an expanded octet. But is that okay? It is, because xenon a big boy and he can accommodate all them electrons. Also for funsies, what is the formal charge of xenon in this structure? Xenon typically wants 8, and how many electrons are around that xenon? 8, and so it has a formal charge of 0, and that makes it like super stable, right? Okay. All right, last one, BF3. So we got a bromine, 3 fluorines. All right, those are 6 electrons, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. We're done. That's BF3. So all the fluorines have satisfied octets, but boron doesn't, only has 6 electrons. Is that okay? That is okay, so we're going to leave it just like that. So which of these have Lewis structures that do not obey the octet rule? Xenon and BF3. But it's okay, because those are exceptions we're allowed to have. So we said that xenon can accommodate more electrons than an octet, but it has a formal charge of 0, and that's good. What about boron? Boron wants how many electrons? 3, and how many does it have? 3, so it has a formal charge of 0, and that's really good, right? So again, it's allowed. It's allowed. Just because it has a expanded octet doesn't mean that it's wrong. It's allowed here. Okay, so of these, which ones are going to be polar? NH4, is it polar? No, because NH4 has a 4 electron domain. That's a tetrahedral. So this is not flat. It is a tetrahedron. But since all of them are hydrogens, they all cancel anyway, regardless if it was flat or a tetrahedron. All right, what about PCl3? Is that going to be polar? Yes, because it is also a tetrahedron electron domain, but one of those legs is a lone pair. So this is actually trigonal pyramid, where that lone pair disrupts It's templating on that tetrahedron, that 4-electron domain. What oftentimes students say, I see it all the time. I'll ask for the electron domain geometry and the molecular domain, right? Electron, they will say, oh yeah, that's tetrahedral because it's 4. But then they'll count 3 bonds and say, oh, that is trigonal planar. No, that lone pair is still there. You just can't see it, right? So these two shapes have to template on each other. Your molecular geometry is always templated on the electron one. So this one is incorrect. It's actually trigonal pyramid, right? All right, next one, xenon F2. How many electron domains? 5. And so what shape is that? Trigonal bipyramid. Yeah, you just gotta memorize it, I'm sorry. So what I like to do is draw the electron domain geometry, right? So I know that's where my bonds and my electrons are gonna go. So then just put the electrons on it and then cover it up and tell me like what shape the bonds make left over. So I'm gonna put 3 lone pairs on a trigonal bipyramid, but where are they gonna go? Are they gonna go in the axial positions, up and down, or the belt, the equatorial? They're gonna go equatorial. So 1 there, 1 there, 1 there. So you can't see the electrons, the lone pairs. So what shape is left over? Linear, yeah. So is this molecule polar or nonpolar? That is nonpolar, yeah. So don't think that if there's lone pairs on the central atom, it has to be polar. That's not true. There are 2 examples where the lone pairs actually cancel each other out. And that is this one. So 3 lone pairs on a trigonal bipyramid, or 2 lone pairs on an octahedron where you get square planar. That's another one where the lone pairs cancel out. All right, BF3, polar or nonpolar? Nonpolar, because everything's 120. Perfect. Okay. All right. Here's another way I can ask questions like this. All right. So I tell you basically how many bonds and lone pairs there are, and you just not guess, but determine the shape. So these kinds of questions are a little easier because you're not having to draw a Lewis structure. You can just make a generic one. So we have a molecule with 5 bonds, so 5 atoms and 1 lone pair. So this structure is A with 5 B's attached to it, and that E is a lone pair. So tell me, what shape is this? Does this structure I drew indicate shape at all? No, we actually have to go through the Vesper theory steps. Okay, so here, how many electron domains are there? 6. So what is that? Octahedral. So draw it in 3D. An octahedron has 1, 2, 3, 4, and then 1 bond coming out, and then 1 bond going back. So 6 electron domains, but how many of them are lone pairs? 1. So I'm just going to draw 1. Where do you want to put it? Because in the trigonal bipyramid, I had to put them in the belt. Do you have to put it upstairs or downstairs? Yeah. Okay, let's put it downstairs. Boom. What shape is left over? Square pyramidal. But for funsies, let's not put it in the basement. What if we put it over here? Cover that up. What shape is left over? It's also square pyramidal. So what does that mean? Does it matter where you put that first lone pair? No, it's not. Okay, what if it was 4 bonds, 2 lone pairs? If it's 4 bonds, 2 lone pairs, we're still octahedral, but now we need to place a second lone pair. So if I put my first lone pair here, where does the second one have to go? Has to go opposite. I can't put it over here anymore because now there's unequal spatial requirements. So you got to put it opposite. And so what's left over now? That is square planar. And so is this polar or nonpolar? That's nonpolar, as long as all the B's are the same on the outside. But if I go back to a square pyramid, is that polar or nonpolar? That's nonpolar. That one lone pair screws things up, but if I make it symmetric like that, you get those vectors cancel. So the square planar is nonpolar, but square pyramidal is polar. I like questions like that. So then you don't have to draw a Lewis structure, but I'm simply just gauging you on, did you memorize those shape names? But remember, the shapes look like what they are, but it's the process of understanding how electron geometry and molecular geometry go together. Okay. I want to be done. Can I be done? All right. You can leave whenever. You don't have to stay. I literally don't care. You don't have to stay. But I'm going to be done. Just look at the key. All right. Good luck, everybody.